Uh-oh. Hang on, everybody. Hang on. There we go. Hi there. How are you? Good to see everyone here, and really excited for our event. Hi there. Good to see you. Just so everybody knows, I like to highlight folks who are in the chat. So just a fair warning about that. Please let me know if you don't want to. That's totally okay. But yeah, I think it's so anyway. Yeah. Hello, everyone. And today we're going to be learning about classification algorithms for machine learning. So let me share my screen and we can get started right away. But before we actually cover any content, it's really important that everyone checks in with our organizing, our organize.mlh.io check-in link. So if you haven't already, please go to the check-in where you can do that for this event. So sometimes I like to ask, where's everybody coming from, logging on from? Not too specific, of course, but for example, I'm logging on from California, USA. Yeah, if you feel comfortable sharing in the chat, please let us know. It'd be really cool to see just where everyone is logging on from. If someone says Connecticut, that's pretty far away from me. 3 hours later, so 10 o'clock evening over there. A lot of folks from the East Coast and North America, some Toronto, Mexico, really cool stuff. And great to see. So, before we get into this, does anyone, and India as well, very cool. Does anyone know about classification algorithms? Want to give us a quick, brief description of what classification means in machine learning? Does anybody know? Yeah, I mean, classification, it brings up the idea that maybe you might have different classes. So yeah, like for example, in computer science, you could have different objects, different classes in your code. It's a little bit different than that, though. It's actually more along the lines of when you might have a job classification, where you would have one job or a different one, but not both at the same time. Yeah, so that's sort of what we're after here is choosing one of many options, and so I want to just one more time plug our check-in. So please make sure to check in. But let's get started. So we actually have some classification algorithms. And these are a few on the screen here. And we're going to actually cover 3 of these categories throughout this workshop series. So we're going to cover numbers 4, 5, and 6 in ours. And Cone says, is it something along the lines of bubble sort, binary, etc.? And yeah, I would say that binary is a really good way to think about classification. Because you're classifying either 0 or 1. And that's really much more along the lines of classification applications. So these are just some of the more common ones. We won't study them all in this series because obviously there's so many. But if you see these words, just know that these are classification algorithms. But today we're going to study one in particular, also a clustering algorithm, number 6, which is K-means clustering. So a classification algorithm takes raw data and predicts its category. So here's an example of a classification algorithm, and it is a fruit classification algorithm. So fruit might have a color, a size, and a weight. And through our classification algorithm, we could design one that will say, oh, well, if it's green and it's the size of your palm and it's like, half, 0.2 kilograms, it might be a pear. And if it's just a few grams, it might be a blueberry. So that would be an example. And let's look at another example. Okay, this is an email spam classification. So with spam email, we want to say, should we put the spam into junk folder or not? And so actually I think this is wrong here. This maybe should say traffic algorithm. I'll get back to this one in a second. This is our spam one. So we have sender, send time, subject, and body. And based on those features of the email, the classification algorithm could tell us if this email is spam or not. We don't want to know if it's 30% likely to be spam. Although that could be interesting information that we can get from a classification algorithm, but the end user just wants it to either go to junk or not. And this one here is a decision-making algorithm. So actually decisions can be classifications as well. So for this one, we have given time of day and the traffic and how much food we have in the fridge and how hungry we are. We could choose to either go grocery shopping or to stay home. And we can't 50% go grocery shopping and 50% stay home. That's impossible. So we have to pick a path. And to do that, we will use classification algorithm. So yeah, a lot of comments in the chat about classification algorithms and how to define them, and really great to see that. So I love to see some chat engagement. Thank you for doing that. And so how do we construct an algorithm specific to our needs? I mean, we have all these different needs and use cases for classification in daily life, but how do we pick the right one for our use case? Well, let's start with talking about what we call type of learning. And can anyone name a type of learning that machine learning algorithms do? Has anybody heard of the concept of learning in artificial intelligence? Okay, so Potato says supervised. That's a really good example. Supervised learning is a type of learning. And someone says unsupervised. That's good. There's also reinforced. Reinforced, a lot of people forget about reinforced, but that is actually a class of learning. And there's also several others like semi-supervised, deep learning, which has also been mentioned. And these are not just buzzwords. They actually have, specific meaning. So let's talk about supervised first. We're not going to talk about all the kinds of learning in this workshop series, but we'll talk first about supervised learning. So supervised learning, it means that models learn from training examples that are provided by humans. So we can use these for discrimination tasks, and discrimination just means recognition, but some people might use that word, and they mean to recognize something and say, yes, that is a X. We split the data into train and testing sets. So we would use some of the training examples to calibrate the model, and other data training examples to actually test the model in what we call out-of-sample testing. And so we typically would see an 80 to 20% split, where 80% of the data is used to calibrate the model and 20% is used to test it. But actually, you can choose whatever ratio you prefer. So here's an example, and we're actually going to cover this in lecture 3 of the workshop. And this has to do with random forest approach. So look at these apples. You can tell that these are apples. In other words, you can recognize them or sort of make a discrimination between these and pears. So yeah, this would be a really good way to classify these images. Okay, here's another type of learning that we're going to cover today. And this one is called unsupervised learning. And unsupervised learning means that the model learns from unlabeled data. And so that means that it would be used for generative tasks, or otherwise known as imagination. So it's modeled off of human ability to imagine something, just like supervised tasks are modeled off of our ability to recognize things. And in this case, we're not really splitting between train test data, at least in some of the more simple examples. And at the end of this workshop, we're going to look at the Kmeans clustering algorithm in Python, which is an example of an unsupervised algorithm. There are some ways to add information to the algorithm, but really it's mostly random and does not rely on us to decide. And the note says it's technically a clustering algorithm, but that means that it puts things into clusters, but it classifies data into set categories or clusters. So it would be considered a classification algorithm as well. And here's an example. This is actually taken from New York Times, where they constructed their own generative adversarial network, which is a type of unsupervised learning. And it created a face. This is not a real person, this face. But it took information like age, eyes, perspective, mood, and it could create a face that looks so much like a person that you might even be fooled into thinking it. What do you think? Does anybody in the chat think they would be able to recognize this image as fake? Some people in the chat. Hi there, Polar Void. Polar Void is really good at Tetris. So if anybody wants to play Tetris, maybe we could play some later. Polar Void will school us all. So hi everybody else in the chat. It's really good to see you there, and I love it when folks are chatting in the comments. It's great to see our community out here. All right, well, let's move on to another one. And this is reinforcement learning. We're also going to cover reinforcement learning during this workshop series. So I'm not in this type of learning segment, I'm not covering any learning that we do not also have an example for in our workshop series. So in reinforcement learning, the model will learn the best strategy using a scenario given by humans. So if I tell the model a scenario, it will, in an unsupervised way, devise a good strategy or an optimal strategy to beat that. And a scenario that we could give it would be actions and environments. So we could say, hey, if you decide to water a plant, then it will grow. And so that would be an example scenario we could give that. And it's mostly used for decision-making tasks. So actually, this type of learning is highly dependent on the scenarios that are given, but the decision-making can be done in a way that you do not need to account for all possible scenarios. The machine learning algorithm can sort of devise a solution. Okay, and someone says, does the reinforcement, the unsupervised learning, use real faces to make the algorithm? And it does. So if we go back to this, the algorithm is called a generative adversarial network. And what that means is that there are essentially two models that are competing against each other. There's one that is classifying, there's one that's building faces, and one that classifies them as either machine generated or human generated. And so there is actually some learning in this algorithm, you know, but you know, there is also unsupervised element to it. So yeah, but the algorithm, the K-means clustering algorithm we will study today, is very unsupervised. So that's a very good question. And someone says, if you use zoom in, there's no clear separation from the bottom row of teeth. So I invite you all to check that out and see if you can spot that. But yes, this is reinforcement learning, and Markov decision process is one example of reinforcement learning, and we will actually use that in lecture number 2. And so I really recommend you check out this YouTube video on Markov decision process by Computer File. It's awesome. I use it to help me prepare for this workshop. And here's just a photo of a robot, which, yeah, robots are really good for this type of learning. So when you are considering which learning mode you should choose, it is very good to try and think of the application. And so unsupervised could be much more of these imaginative, generative tasks, such as imagining pictures of faces, writing. So everybody now knows about ChatGPT. ChatGPT has some imaginative, unsupervised aspect to its learning. Then we have on the supervised case, if you want to do something which is discriminative or recognition task, that could be a question and answer or recognizing a speech pattern. Have you ever called a customer service line and they recognize your voice? That is example of supervised learning. And then we have some that are in the middle. So I would describe reinforcement learning as somewhere in the middle of these two, where you're trying to make a decision. And this Venn diagram also says if you want to make an image caption, for example, it could be somewhat in the middle of the two. So does anyone have any questions about selecting the learning type for your algorithm? There are other types of learning. Do not want to make it seem like there's just supervised, unsupervised, and reinforcement learning. But those are all we're going to cover for this workshop. All right. Well, why don't we move on to the next segment of this lecture? And remember, at the end, we're going to do some real example of machine learning. So that'll be really cool. But for now, we're just sort of getting introduced to the concept of classification. All right, so someone says, depends on the inputs you have, the outputs you want. Exactly. That's a really good way to put it. If you have some human trained or human labeled data, might be really good to consider supervised learning, but you also might not have that. And so you kind of have to also maybe limit your choices based on the models and features and needs that you have for the project. And we're going to talk about a lot of that right now. So these are some other factors you should consider when choosing a classification algorithm. And one of them is the number of features. So how many variables do you have? And this could be things like age and height for a person, or for your fruit, it could be the weight, size, color, sweetness, maybe calories. So you could have so many variables. And actually, if you have more variables, then there's a better algorithms to use for that, such as support vector machine, which is very efficient with high order data. Then on the other hand, if you have a low number of variables, you might want to choose a classification algorithm similar to decision tree algorithm. So decision tree algorithm is based on it could be based on a few variables. Like in this example, there is a disease classification, and it says the age of onset, for example, is one variable, and so that is a very good way to illustrate some concept in an intuitive way with just a few variables. In the support vector machine, essentially draws a surface that divides the two sides and classifies that way. Whereas in the decision tree, the idea is to have these threshold values. So, for example, there's is the year of onset 8.5 or higher, and you can get yes or no, and it will put you into a different tree. So these are just different models that folks have come up with different strengths. Oh, and this, let's look at this little sticky note, which says, can you reduce the number of features to simplify your model? And that's what we call feature selection. We'll be covering feature selection when we study random forest model. Feature selection is a really tricky process, but really important to both simplify the model, reduce overfitting of the model, which occurs when you have too much data or your model becomes too closely fit to the data, not too much data. Sorry about that. And the next factor we will consider is linearity. So is your data linear? What is the distribution of your data and the relationships in your data? That's really important to know. For example, if you have linear data, you could consider support vector machine, which is SVM. But actually, if you have nonlinear data, a decision tree could be better. So yeah, some of these models have multiple strengths and multiple weaknesses. So these are the same models we saw in the last slide, but now we're looking at them from the perspective of whether the data is linear. And we'll actually talk about linearity and nonlinearity in our example today. So you'll get some practice looking at linearity. There's another aspect. So training time is important as well. And that means how much data do you have and how fast is your computer? So if you have, are you only using your laptop, or do you have a supercomputer somewhere tucked in your room? Or maybe you have a virtual connection to one. And that could mean the difference between using a faster algorithm like logistic regression, which is very fast, or one like random forest, which we will work with in our random forest lecture, that could actually take much longer. So these are things you could consider. And generally speaking, more training, it means more accuracy, but that's actually not always the case. So yeah. It is generally good to train longer, but that doesn't always mean that you will get a optimal model. We could consider the number of parameters. And so parameters are really how we make the model flexible to our needs. And so in logistic regression, there are just 4 parameters that can be changed. But in K-means clustering, 8 parameters could be changed. So there's a lot more options for the user. And if you have a supervised algorithm, you can split your data into train, validation, and test. So you can actually create a third category called validation, where you will tune these parameters by tweaking them slightly to see whether you get a better outcome before you test. And yeah, that is really up to you how much training flexibility you want for your algorithm, for your model. All right, everybody, we're going to take a 10-minute break. And then after the break, we're going to return and we're going to actually do an example where we work with K-means clustering algorithm. And I'll send you all a Jupyter notebook, a GitHub repository with Jupyter Notebook. And so, yeah, if you don't have access to Jupyter Notebook, please, during the break, I'm going to send a link in the chat to anaconda.org, where you can download a Jupyter Notebook environment on your computer. So that would be a great way to spend your 10-minute break if you don't have Jupyter Notebook, because otherwise you'll just have to follow along, which is totally okay. But it's also fun to do it on your own. So I'll see you all in just 10 minutes. Bye-bye. Hey everybody, and welcome back. After the brief break, I see a lot of you stuck around for our Kmeans clustering demonstration, and I also saw a lot of comments in the chat about different products for doing Jupyter notebooks and sending links to folks who need them. It's really great to see everybody being so helpful and kind in our community. So thank you for doing that to those who did. And yeah, why don't we move on to K-means clustering now? So K-means clustering is a clustering algorithm that categorizes data into K groups, and K could be any integer. So it could be 2 groups or 3 groups or however many you'd like. And then initialization is totally random, which means that our answer will be slightly different each time. So the centroids, which are these black X's in the diagram on the right, those centroids will be placed in kind of a random place. And then every iteration, they're moved to minimize the squared errors from the centroid. That's really the machine learning algorithm. I mean, most machine learning algorithms work in some way like that, where there's some optimization goal. There are others that don't, but there are a lot that do. So in this case, the optimization goal is to minimize the squared errors, or in other words, the distance from the centroids. So here's some examples where K-means clustering has been accomplished. And on the right, you can see these. They're actually from the scikit-learn or sklearn documentation. So yeah, these groups of data have been classified in clusters of 3. And some of the assumptions are that there are K clusters to begin with. So if you want to use K-means clustering, you have to know how many clusters that you want. And another assumption is that the features are isotropically distributed. And what that means is that they kind of are the same in all directions. And you can see that some of these examples don't follow that. For example, the top right plot is not isotropic, but it's pretty close. And that sort of goes along with the spherical variance, where you have kind of these spherical shapes. And yeah, as we mentioned, even though the top right plot is not really very isotropic, there's flexibility in these assumptions. So the K-means clustering will work, generally speaking, even if not all of these assumptions are strictly defined or strictly met for your application. So we're going to do an example, and this is the link to the GitHub repository for our example. And yeah, go ahead and visit that link. I just pasted it in the chat. And so someone asks, what does isotropically distributed mean? So actually, let's look at the Wikipedia page for isotropic. Maybe that will help us a little bit. Maybe not, actually. There's a lot of different branches from this, and none of them have any pictures. Well, let's look at the example, and we'll see. Oh, people are getting an error. All right, let me try another link here. Oh, you know why that is? It's because the repository is still private. Sorry about that, everybody. Let me quickly make it public, and then it'll work for you. Change visibility, change to public. Okay, the repository is now public. So if you refresh your page, actually, yeah, it should work now. That's great. And I'll paste the new link, which is a little bit simpler link. or actually, it's actually the same link. Sorry about that. But let's talk about isotropically distributed. So let me try and find an image for you that would be good. Isotropic means that essentially in all directions it's the same. So in the example on the top right, this direction, this like diagonal direction, is very much like more pronounced when you compare it to the other direction. In these spherical examples, like in a baseball, for example, no direction is preferred. No direction is distinct. All directions are the same. And that's also true of our spherical clusters. So that's what we mean by isotropic. Yeah, sorry I couldn't find a diagram. It's actually kind of hard to find a diagram for some reason. But yeah, let's work on this. And actually, you're going to want to navigate to lesson 1 blank .ipynb. And so this is the blank version of our lesson today. And we're going to work from that page. So yeah, why don't we go ahead and start? So I'm going to share my screen and show you all the code. And you can follow along on yours. Okay, so here we are. I'm actually using VS Code for our notebook. You're welcome to use Anaconda or Google Colab, all really good tools for Jupyter Notebooks. But first, we're going to start by importing the necessary libraries, and that is going to be Pandas, NumPy, PyPlot, and sklearn. And so you might be familiar with these libraries if you are familiar with data science. And I also have a workshop series that's published on YouTube called Intro to Data Science with No Machine Learning. And we go over these packages in detail. So if you're not familiar with them, you can visit that workshop. But if we run this, it'll import all of our libraries, hopefully. And yes, it does. That's awesome. So yeah, you know, you can do this as well. Follow along. And now we're going to look at a standard K-means clustering example, which is actually inspired by an article published on rposts.com. R is another statistical analysis language. And so you could totally check that one out. But yeah, we're going to modify this slightly with our code. One, we're going to be doing this in Python. So I've adapted all of the code for Python. And two, we're going to get into some interesting features of this. So first, we're going to load the data. That's the most important thing. We need to actually have a data set to work with. So I'm going to use df to represent a data frame. And we're going to use read CSV to read in a CSV file and as a data frame object. So we're going to use the faithful.csv data set. And if we look at this, it has a table of values. These values are volcanic eruptions from a geyser in Yellowstone National Park. Or I'm sorry, actually Yellowstone, yes, that's correct. So let me show you a picture of Old Faithful. We're gonna go check it out. Okay, so here's Old Faithful, this cone geyser at Yellowstone. Check that out, everyone. I mean, these are people, and that geyser's going maybe like 20 people high in the air. Here's the image for you all, so you can look at it. Back in 1948, it's almost 100 years ago now. In 25 years, that'll be 100 years from now. Kind of remarkable. All right, so we're gonna now go back to our code, and so basically this data set was taken from that geyser and just someone recording an eruption So for example, this first eruption lasted 3.6 minutes, and it occurred 79 minutes after the previous eruption. So, all of those eruptions are logged. We have 272 of them. And if we visualize the data, which we can do by using our matplotlib, we could just do a scatter plot, plt.scatter, of eruption versus waiting time. We see some interesting data here. And we see kind of these two clusters forming where one kind of eruption happens very soon after the previous one, like 50, 60 minutes before. And it's a pretty short eruption, like 2 minutes. And then there's another kind of eruption that happens like every 90 minutes. So it takes longer to build. But once it happens, it does it in like 4.5 minutes long. So the eruption takes a much longer time. And in between these kinds of eruptions, like let's say for 3-minute eruptions that happen every 70 minutes, there's not much there. And so we could hypothesize as the data scientists that there exists some cluster. There exists 2 clusters of data, and we want to be able to classify eruptions as they happen, either as big eruptions that happen far apart or as tinier eruptions that happen closer together. And we are going to use the assumption that there are these 2 groups of data, and then we can test on new data whether they would fit into the long eruptions or the short eruptions. So why don't we go ahead and try this one? And we're gonna do that. The next step is going to be to format our data to be useful to the K-means model. And so if you use df.values, that will actually put the data in a form that's usable for the K-means clustering algorithm. It creates paired lists where all of the data for a particular eruption are paired together in a list. So you have the eruption feature and the waiting feature both in the same list for each example. So yeah, now our data is in the proper form to be analyzed by the K-means clustering algorithm. And if you're interested in looking at the documentation for K-means, we have a link in our notebook so you can check it out on scikit-learn's website. But in a nutshell, the K-means clustering algorithm requires that number of clusters and not much else. So if we type K-means just to create a new K-means model, we have a little parameter list that pops up, and the first one is number of clusters, or n clusters. And so obviously, we already talked about clusters being 2, so we're going to set this to 2. And now we're going to initialize our centroids, and actually that might not be obvious because we haven't talked about that yet. So I'm going to use the init equals random method, which is going to randomly place those black X's that we saw earlier, those centroids, at random positions across the range of the data. And you can use a more specialized algorithm in this case, but our data set is small, and it probably will not speed up the code to place them in strategic regions. But you could if you wanted to, and the improvement would be in the time to fitting, not necessarily the accuracy of the fit. So next we will have maximum iterations, and we want to specify this because we want to make sure that the model doesn't just go on forever and ever or take up too many resources. So I'm going to specify maximum iterations to be 300. So after 300 iterations of the K-means clustering algorithm, we're going to say, you know what, it's time to stop with this and yield the result. So let's fit the data now. We can actually run this by typing kmeans.fit And then we will place the X, which is the feature list, as the argument in this method. And we get a K-means model object. So this is a specific trained model. And so this is unsupervised. So we didn't tell the computer that certain eruptions were either category 1 or category 2 eruptions. So it's unsupervised. All we told it was, hey, we want you to find 2 clusters and make it happen. So this is what the computer came up with. It came up with this fitted model object, and we want to know the results of our fit. What happened? I mean, that was really quick. It took 0.1 seconds. What just happened? Well, let's look at some information here. So we have a lot of attributes that we can call. So one of them is cluster centers. So here is cluster centers. These are the 2 centers where the centroids ended up. So the first centroid ended up at 2.1 minutes eruption time and 55 minutes waiting time. The second centroid ended up at 4.3 eruption time and 80 minutes waiting time. So these are kind of interesting that this is where they lie, these 2 centroids, kind of what we predicted in a sense with our eyes. And now let's look at the Kmeans.inertia variable. And so this one is actually kind of hard to interpret for us. It's the sum of the distances of all of the points from the centroid. So this is actually the variable, the statistic that the algorithm is trying to minimize. It's saying, how small can I make this number by tweaking the position of the centroids? And so if you added up the distances of all of our data from these 2 centroids, it would be 8,901. I guess that's minutes. But yeah, we want to minimize that value if we are the K-means clustering algorithm. So that's kind of an interesting thing to try. I mean, in a sense, this is the model score. It's kind of how well the model did. And if we were able to run it again, let's actually fit the model again. We can do that twice. Yeah, well, I guess we didn't change anything about the model in that situation. Let's see 3, for example. Yeah, so 3 gave us a better fit. But we're not so sure there are actually three clusters. So I'm going to actually put this back to 2. So that's one way you have to be careful when you're minimizing. This inertia parameter is not super useful to us as humans, but very useful to the K-means clustering algorithm. And the next we will talk about is labels. Actually, before we get to labels, a number of iterations. So I wanted to point this one out too. So it took 5 iterations for the K-means clustering algorithm to reach its optimal state, where it wasn't actually updating anymore. So it only took 5 tries for this algorithm to pick the right centroids. All right, now we're going to move on to labels, which is probably the most important of these. And so this is actually where we see that the data has been properly classified into either one category or category 1 data or category 0 data. And so all of the eruptions are assigned either 1 or 0. And I'm going to actually store these. I'm going to call it flags, just to note, it sort of flagged which data were category 0, which data were category 1. All right, so now we're going to plot this data, and we'll see what happens when we do that. So I'm going to write category 0 for one type of data. This could be the short ones or the long ones. We actually haven't looked at the data and seen, but I think the centroids tell us that 0 is the short kind. So this would be a df and flags equals 0. So we're going to mask all of the data in the eruption set and choose only the values where flags are equal to 0. All right, and the next one is flags equals 1. That's the next category. And so these are the 2 types of data that we have. And we can plot them with a scatter plot. So let's plot first our category 0 data. So we have category 0 eruption, category 0, I think it's waiting. Yeah, so here's our data for our short volcano eruptions or geyser eruptions. See, they only go up as high as 4 minutes long, and they never get past 70-minute intervals. But if we plot our category 1 data as well, and let's be sure to label these as well so we can tell them apart. We see that there are two distinct categories. And so the K-means clustering algorithm has grouped our data into category 0, which is these short eruptions, and category 1, which is these long eruptions. Right? And we can actually predict a new eruption. So check out the notebook. It says, now imagine we see a new eruption. This one lasts for 3 minutes and came 75.2 minutes after the previous eruption. So in other words, we know that our new eruption was 3 minutes and our new weighting was 75.2. And so if we wanted to predict, we could use our K-means algorithm. And there's actually a method in here called predict. And we can type new eruption, new weighting. And it tells us 1. It doesn't tell us 0.5 or 0.8 or some number in between 0 and 1. It basically classifies the data into a long eruption. So even though this is a 3-minute eruption, which is kind of short by category 1 standards, it actually gets classified as a long eruption. So interesting. Someone says theirs was a category 1 and then it became a category 0. That's kind of interesting. I'm not sure why that would happen to you, but maybe the algorithm is very slightly different. I chose deliberately a very borderline eruption to see what would happen. So maybe it's possible to get a 0 if you have a slightly different model than the one that I have. So that could totally be possible. All right, now we're going to move on to a non-spherical clustering example. And this is where it gets interesting because we're looking at an example that is non-linear. So we're going to be looking at some fake data, which is imported from this CSV file that I've created called Bullseye. And imagine that these are just hits from your school's archery team practice on a bullseye target. So maybe you had a bullseye and your archery team was shooting at it, and then these were the results. So let's read them into our data set. And when I originally read in this data file, there's this unnamed column that I don't really want. So actually, I used the brackets to select X and Y only, so that it would just only take X and Y, which are just the position of the hit. So the first hit was at negative 0.42 X. If you could maybe say meters, this is just like meters to the left, I guess. And this would be negative 0.01, which would be like 1 centimeter below the bullseye. So yeah, why don't we go ahead and plot these to see what they look like? So we could plt.scatter if X and Y. We could see that this is the bullseye. And yeah, it looks like a bullseye, right? And we have three clear ranges. So maybe this bullseye here was like 15 points. This one was 10 points. This was 5 points. We have 3 categories of hits. And let's say we wanted to sum up the score of the whole team. It would be pretty hard to do that if we couldn't classify these hits in an easy way. So we will go ahead and do that now with our K-means clustering algorithm. And I'm going to actually just copy and paste in the code from the answer key because it's the same exact thing that we did for our faithful geyser code, but just adapted for our bullseye example. And when we plot this, we get a classification, just like we did for our previous one. And the K-means clustering thinks that these are the three most natural categories for our bullseye data. It says that data in the top left is category 0, data in the top right is category 2, and data in the bottom is category 1. Yeah, but does anyone see an issue with this? I mean, why is it unable to classify our bullseye correctly? After all, our data seems to be isotropic, and we're asking it to give 3 clusters. It seems like it satisfies a lot of the assumptions of the K-means clustering algorithm. So what's with that? Any ideas from the chat? Yeah, it seems like some folks say, are they linearly separable? This is a really good question. Kind of alluding to what we might be doing in the future. So let's actually get into this and see if we can transform our data and get a better result. So for one, this data is not rectangular and there's no spherical clusters. It's actually polar. So you may have studied polar coordinates when you were in school. And essentially the polar coordinate system, let me paste it into the chat and we'll actually go there ourselves to check it out. The polar coordinate system relies on 2 variables. You have r, which is the radius or the distance from the origin, and you have this angle, which in this diagram is phi. Let me paste it over here. But in our case, it's theta. I just called it theta just to call it something different than this diagram. But if you have r and theta, then you can get the correct point instead of using x and y. And there's actually an equation to convert between the two. So these are the equations. You can use r can be the hypotenuse of a triangle that is formed by x and y. And theta or phi you can get by using an inverse trigonometric function like arctan, for example. And so, I actually went ahead and did that. So we're gonna transform this data into polar coordinates for you all. We're gonna do it live. Hopefully, I can remember. So R, we're gonna create a new column in our data frame called R, and R is going to be dfx squared plus dfy squared. And then we're going to do the square root, which is to the 0.5. And I actually just remembered that this caret symbol is not how you do exponent in Python. In Python, you use 2 ampersand keys. So I'll have to write that. But now if we write df, we have a third column, and this is the radius. So actually, how far is this hit from the center of the target? All right. Now we're going to have our theta, and theta we can create, and the Wikipedia page. Sorry about that. So thank you for sending. Thank you for sending a message about that. I'm glad I was able to catch it pretty quick. Thanks to you all. So yeah, theta is actually, we can use arctan. I think it was y over x, if I remember correctly. I also use a different one in there. Actually, I think I'll use the one in the example that I have because I know that it works. I use arcsine of y over r, which is another polar coordinate transformation. But now when we print our data frame, we have the angle as well. So, now let's go ahead and try our example again. And someone says, how do you define the center on a 2D plane? That's a really good question. So let's look at our graph again. Oops, I thought that would zoom in for me, but actually it doesn't. Can I do this maybe? Yeah, that's cool. Okay, so you can see on our 2D plane, the center is 0, 0. And that's the default for polar coordinates. Let's go back to the Wikipedia page and check out that. See that the Wikipedia page says that 0, 0. Here it is. The origin is the center. There's the picture. All right. So yeah, that's the origin, 0, 0. And it also matches our bullseye example. So if our data wasn't at 0, 0, we could always subtract a fixed number from the data or normalize the data, and that would bring it to 0, to have its average value at 0. But that's a really good question, so thank you for bringing that up. Okay, so now we're going to move on, and let me remove that. That's actually the wrong, I just shared the wrong thing. And we're going to go to this next line of code, which is going to be another K-means fitting. And we're going to, before we fit actually, let's plot this data. So now that we've transformed our data into polar coordinates, where we have r and theta, you can see that we have 3 distinct boxes, and the data is now could be approximated by a sphere. So it can actually create a centroid at the center of each of these and kind of draw values into that centroid. So that's what we're gonna do in our K-means fitting. So let's copy our K-means model from before. And now we're using r and theta instead of x and y because we need to account for the polar nature of the data. And when we run this, look at that, we get 3 distinct categories. Isn't that pretty cool? So now we get a 0, a 1, and a 2 category that actually makes sense. So it's kind of like magic, but it's not really magic. And, I'm going to leave it as an exercise to you all to figure out what the score of this archery team is. Yeah. So yeah, maybe go ahead and try that on your own. If the point values are, like we said, 15 at the center, 10 in the middle, and 5 on the outside. So I'll come back with the answer for you in the next workshop. But now you're officially a K-means clusterer. So congratulations, everybody. I'll send you the congratulations emoji in the chat. Hang on. I'll send you one. Okay, there it is. So congratulations on your status as a K-means clusterer. Does anybody have any questions about what we covered today? We covered a lot of information. We covered how to choose your classification algorithm based on what you want to do. In this case, we wanted to classify data, and we actually used an unsupervised learning approach, which was customizable for our data. And in other cases, you might want to choose other algorithms, and that's why we're going to continue this workshop series with more parts. But yeah. Well, thank you so much, everyone, for joining today. And that concludes for today's workshop, and I'll see you next time. Thank you.